Okay, welcome back. So, 2 more lectures to go. 1 more working group for most of you, or all of you. And then just the final project. As you can imagine, in order to give you also time to work on the material, there is not that much new theory coming, but there's still 2 very important topics, I believe, worth coming, and also questions that we're going to, topics that will be relevant for the exam, and that is the ethical implications of doing AI research and the philosophical questions that occur around the topic. And I will lead a brief discussion on ethics in the second half of today. And Frank van Hamelen is coming tomorrow to talk for 1 hour with you about the philosophy of AI. And that is, in my experience, one of the highlights of my year, at least, when this discussion happens. So Frank is one of the few AI researchers and members of the KNV, so the fellow of the European AI Research Council. So he's one of the most foremost researchers in AI, and he's talking about philosophy of AI tomorrow. So I really hope you will all show up and come and enjoy this. Still, there's one last thing I want to talk about, and that is now what you can do with these neural networks that we discussed yesterday to make them as powerful as they've become the past years. So the idea here is that you make them deep. And deep means that you add several layers of hidden layers to your network. And I will explain a little bit about that in the first half hour or so in this lecture. First, I want to start with some organizational matters, if that's needed. And that is, as last time, the question, is there anything that needs to be addressed? Is there anything that is unclear? I will talk about the practical project shortly before the break, so that we have an opportunity to really be sure that you know what you have to do. But is there anything else we have to solve? Do you think you have sufficient support for your programming? Is there anything else we can fix? Yeah?
I just had a quick question about the project. So it says on Canvas specifically that there's a 10-page limit, but in the slides it talks about a 12-page limit.
Oh, good point. I'll fix that. So I think a 12-page limit is more appropriate. But I will publish some more details about the paper and the reviewing process later. So probably beginning of next week, how to write this really. So the question was, I should have repeated that before, that there is a discrepancy between 2 bits of information that we provide about the length of the document to submit between 10 pages or 12 pages, and also about, I guess it's not very clear yet which format for the writing of the paper to use, and I will communicate that beginning of next week at the very latest. Yeah? So then I have a point of organization, and that is that you can imagine that given all the material that we have covered the past 11 lectures it is now, this is very difficult to cram all the material into 3 working groups. And in particular, this material on learning with gradient descents sort of doesn't fit into the 2 hours that you have tomorrow and on Friday. So we've decided to focus on the remaining part of the material, so fuzzy logic, Bayesian learning, probabilities, to cover tomorrow and Friday in the working groups. And I will use half an hour of tomorrow's lecture to sort of interactively go through an example as if we were a big working group, because I mean the group isn't that big anymore. We can still discuss things. So there will be actually homework. I will put it online after this lecture. And I really recommend that you look at the exercise about gradient descent learning and then we calculate it through here together in half an hour tomorrow at the second half of tomorrow's lecture. Yeah. So I will put that on the assignment online, and there are some things you have to fill in about. It basically is about derivations and applying the ideas of the gradient descent learning to find the optimal hyperplane for some practical problem. Yeah. So although this material won't be covered in the exercises of the working groups, it will still be relevant for the exam. That is a very important announcement here. Yeah? But we will discuss it tomorrow. Okay, let's start with the real topic of the lecture, and that is deep learning. And I tried to explain yesterday the basic idea of the neural network. So you have some input nodes that propagate some information to either an output node or some hidden layer with some weighting. And it's these weights that you can learn by checking whether your prediction on a given input is true or false, or good or not so good. And if it is good, if it's overestimating the result, if you do a regression problem, if it's overestimating, then you reduce in a very limited way the weights of the nodes that gave you the results in some back propagation algorithm. That's the general idea. If you have a perceptron, which is just a linear classifier, then there are certain things that you can't really learn with your network. So you get some extra hidden layers which allow you to do this. And this was very popular in the 90s, up to a moment where sort of the AI winter and the neural network winter occurred, because people sort of understood that you could do quite a lot with those networks. But there was one big problem, and yesterday I said that the biggest problem was computationally, because if you consider a deep or a big network with lots of hidden layers, then each of those layers becomes a parameter in your optimization space where you want to find a solution. And so my statement yesterday was that it was particularly a computational problem, but it's even more importantly a data problem. So if you have these many dimensions, then the gradient is not very easily detectable anymore. It's not very clearly leading to the optimal solution. So there are many local optima, and you need a lot of data to really train your data set, your network properly. So it was more the sort of the lack of training data or the tuning that really became a difficult problem that made it difficult to work with these networks at the end of the millennium. So what was the promise? Why did people care, and why did people continue work on this? Was the promise that if you would now stack layers of hidden layers on top of each other, you could maybe use different properties of the data and different properties of these layers to stack information that could be found and learned by these networks. So the idea was, the hope was, that the lowest level could sort of reduce the precise information about the pixels to some broader information about the shapes of the faces, so the important features of an image. While an intermediate level would maybe look at parts of the image. So each of the layers would take over some specific property of the learning process. And then the high level would then be sort of learning the classes for a particular image or a part of an image. So the depth of the network was related to some different properties of the learning process. The problem, though, is that if you do this, it's very, very complex. So if you approach this naively, you would have an input layer, and then you have several of those layers, and basically the tuning of the parameters doesn't work anymore if you do it in a naive way, because the gradient can't be calculated that easily, and it doesn't sort of give you a good direction to do your search in, and the huge number of parameters is difficult to train. And there are basically two solutions to this. The first solution is pre-training, and the second one is called convolutional networks. And I will briefly give some intuition about this. Not being an expert, I'm sure you will hear more about this in the machine learning course next year. For me, you get sort of a peek preview to get some general idea of how this works. Basically, the idea is related to something I did last time, in the last lecture yesterday, and that was the autocoder idea. Namely that you took an image as an input, you trained a neural network on itself. So it's an autoencoder. You train a network where the output is the same as the input. And basically you try to find the image itself, you find it back, while you change the dimensionality through the hidden layers. So then you change some of the features of your input by adding more information or sort of focusing on other information. If you, for example, have a smaller hidden layer, then you have a dimensionality reduction. And this allows the training algorithm to focus on certain of the properties. So basically you start with an image, you do some an autoencoder on some larger hidden layer. Then the idea here, which makes then in the end the difference, is that you can now stack these autoencoders. So basically, what's interesting is that if you do this autoencoding, there is a hidden layer which carries some meaning. It carries information about the training examples in a higher dimensional space than the input was. So now you can take this hidden layer as the input to a new training problem. So you change the information by adding a dimension, and now you do this exactly the same. You do what used to be the hidden layer is now the input to your new network, and you change the dimensionality again, for example, reducing it, and you train it on itself again. So you do some pre-training on hidden layers where you try to reproduce the same results, but in a different dimensionality. And then you do the same again. You train a network on the third layer, and you change the dimensionality again. And then what you can do is to stack these hidden layers on each other, on top of each other, building a new network, now a very deep network that sort of changes the dimensionality. And the interesting thing that comes out of this process of changing dimensionality through these hidden layers that are sort of piled on top of each other is that when you now reduce this to a binary space, the images that are similar to each other occur on different parts of the feature space. So in this example, the hope is then that if you do this autoencoder idea in different layers, that at the end, you basically reorganize your images according to some properties, according to the different layers in the different parts of your feature space. And this, if you now put this into a standard training, it will allow you to do the separation again between the similar images and the non-similar images. So this is how this works in practice. This is the example from the digit recognition training sets, or one of the classic data sets, MNIST, where you have as input the different digits, and so without any training, without any human input, these different layers manage to separate the different classes of input data. One thing I should have maybe made you're aware of is that in this scenario there is no pre-classification by humans. It's a non-supervised task because we always use the output and input is always the same. So we train those networks on the data itself without any labeling, but through the dimensionality reduction, they end up at different clusters in the feature space. And now for another classifier, it's easy to recognize these different classes, that these are now similar objects. So this idea of the autoencoder and putting one on top of the other really allows you to separate the similar cases before you even come to the classification problem, and makes the classification problem far easier. So this is really the sort of the implementation of the hope of the deep networks, that each parts of the networks do their own little magic to come up with the separation of the classes on the top level in the end. Here is another example where they put in newswire stories about certain topics, and I think they started out with 500 features, reduced them to 250 with one training. So again, you took as input, you took the feature representation of the newswire stories, you reduced the dimensionality with an autoencoder, which you trained on the same input as output, and then you took the 250 features of the hidden layer that you got, again, as a training, as the input to a new autoencoder, and you reduce the dimensionality again. And when you then come up to a very low dimensionality, you get those clusters in the space that now can easily be detected by a standard classifier. And usually they are then again fed into a neural network because that's the way they are automatically done anyway. So it really is the trick of this approach is to really apply many layers of hidden layers stacked on top of each other, where each of them sort of help you reduce the dimensionality and therefore help you identify unique features of the input data. So in principle, the first step is then unsupervised. You create those stacked layers of a neural network, a deep layer network that helps you build those intermediate nodes. And then after that, you stack those things together. And this network now helps you to do the classification that you want to, that was your original task. So that was the idea of pre-training, because pre-training means that those, the red and the green nodes, have been pre-trained by some unsupervised learning in this first phase, where we just used stacked autoencoders, one on top of the other. And this has shown to really introduce this depth to the neural network approaches without necessarily producing the need for tuning all the parameters in this network, because it's already done on the data itself. So that's one approach. The other approach is pruning the network, and the core problem is, of course, that in principle you build the network by connecting all the layers, all the nodes in the layer with all the other nodes in the next layer. So if I have, what is it, 2, 4, 6, 8, 10, 12, 16 nodes, I have to connect them to all the 16 nodes of the next layer, and you see that this is already, gives you an enormous amount of features that you would have to optimize to find the perfect solution for. So instead of doing this for your network, you look at interesting combinations of nodes that you can connect to the nodes of the next layer. And that's what's called the convolutional neural network approach, where the idea is that you say here, let's look at the idea of image classification. The 4 pixels that are next to each other, they might contain some meaning that is related to each other. So the standard thing would be, we have an input layer of, in this case, 25 nodes. And if we would connect those to a hidden layer of, I don't know how many, how many nodes in the hidden layer, we would have to connect all the 25 to each of those hidden layer nodes, and that would create the many weights to train. So instead what we do now is we say, okay, the 4 ones on the top, they sort of contain information, and we just combine those and give the output value of their what's the word? So their output value to one node of the hidden layer. And then we do the same with the neighboring 4 nodes, and so on. So basically for these 4 possible combinations of 4 nodes on the right-hand side, we get now 4 layers. And basically then the idea is we do this for all of them, so you have these 4 here, and for each of those rows we have another 4. So we get a hidden layer of 16 nodes, and each of the 4 nodes is only connected to its node on the higher level. So instead of now having a connection of these 25 times 16, it would probably be, that would be the original one, we just have each of the nodes connected to 1. So we only have 16 weights that we now have to train. Yeah. So what you can then do is that you do this several times. So you add not one of these layers, but you add more of those layers in exactly the same way, which allows you then to train your network. So basically, you again then stack these this reduction of the original nodes that you have to some more collections of nodes, and you stack that one after the other. So there is an intermediate phase which is just pooling, which is called pooling, which I have to check what it means because I've forgotten. These are built, they contain no weights. So these pooling layers just pass on the maximum value of the nodes they are connected to. And I cannot tell you why this works. I guess that a true machine learning person has some intuition about it, but it sort of stabilizes. My guess is that it stabilizes the process to have these pooling layers in the middle, which just takes the maximum value from your input values and passes it on to the next layer. So basically, you stack those convolution layers up to the point where you come to a very low-dimensional neural network again, and basically you can then train on this one. And this works extremely well. So given that you have these different convolutions for these different convolutions for the image, so when you remember when I showed you how to reduce those 4 nodes in a square to the 1, I said that you can build more of those, and the network is sort of multiplying these layers. Then each of those will learn some kind of approximation of the image. So in a way, you blur down the image, the original image, and the result, if you combine those in different layers, is some kind of filter. And if you then look at the image after this filtering process, then it seems rather blurred. So at first sight, you might think this has lost a lot of information because now it's far less crisp than the original image is, or the original image might be. But the advantage of this is that it really focuses on the essential elements of the image and has taken out everything that is sort of considered noise or can make the classification less clear. Here is an example of how these different convolution layers work. So you start out with an rigid set of images, you make a linear transformation, and you apply the first layer of convolution. If you visualize this, you see that there are parts of the image that sort of are represented. You combine those, another layer of convolution, and it helps you learn part of the image. And again, if you go one level higher, it helps you sort of learn blurred versions of representations of the images that you had in training. So each of those convolution layers gets you a different aspect of the learning process. And this was really, these two things were the technologies that changed the neural network world since the years 2000. So there was an early success in 2012 from Google, where they started to really find cat images in videos, and that was based on this technology. Something that we wouldn't have considered possible 10 years ago, even, is natural language descriptions for images, things that are now also done. There is an interesting, funny demo where you can take an image as input and you apply these ideas of convolution of different ways of representing parts of the, or different aspects of the image, and you can use them to change the style of the images. So this is all done automatically. You sort of have a Monk style and a Van Gogh style for the same image that you put as input. So it's quite nice to play around with this. But the interesting thing is here that this is really on a standard classifier neural network trained and not sort of purpose built. But it basically allows you to transform one image representation to another one, which then has specific properties. It's quite fun to play around with, but and I think this is the thing that I think is really the coolest of the, and it's also very recent, is a result that you get with these deep networks, and that is you fill in, if each one goes here, you fill in the left-hand side and you get the right-hand side as a result, so 1, 2, and 3. And so this one is still sort of, I can imagine you make an abstraction from an aerial view and you get the map. But look at the top one, you get a representation as input of colored and very abstract things, and the neural network produces really images of cars for this. Or the output, you have an input as a black and white color, and it gives you a colored image. Or this one, you have a really sketch of some object, and you get a fully filled in image. So it's sort of the other way around. What we thought might be possible 10 years ago is now even possible, that you enrich your information according to standards that you have learned before. And then we have our example of AlphaGo, where, as I said yesterday, there are basically two things you can learn about such a game. The first one is the policy network. That means where do you put your stone in the next decision moment you have. And the other one is the value network, and that means give me a position and tell me how good it is. And in AlphaGo, both are trained using these deep neural networks at each of the moment, where basically then the networks contain information about parts of the board and combines them in the different convolution layers to some more high-level information about the policies. So I think this was all I wanted to say about deep learning. I hope that I've made you a little bit curious about it so that you go to the machine learning course next year. I'm not very sort of convinced I did a good job at explaining all the concepts, but I think it's important to mention it, and I think the intuition that you might take home today is really this idea of if you stack if you have these huge networks with several layers, that the complexity of finding the best solution is really so high that your search algorithm can't find the optimal solution to the network problem anymore, to the learning problem anymore. Still, that the stacking of these layers of the network, that this can be really very powerful, and that the new techniques that have allowed us to do this are the pre-training, that you train the different layers through this autoencoder idea, and that was number one, in an unsupervised way, so that's usually very cheap. And the second idea is the convolution neural networks, where you look at local properties of your problem space and try to find reductions of the connections between the input nodes and the intermediate nodes at each of the layer, so that you sort of cluster bits of information that are relevant for the learning process and avoid doing the full search over all the possible parameters that you have, that the full network would have. So these are, I think, the basic ideas, and I hope that you get those after this half hour. So let me go back now from the deep learning, because in a way what we do for our project and for the working sheets that you got yesterday, it doesn't really matter what kind of learning algorithm and method you use. There are many tools around, and whatever tool you use, it doesn't really matter for the problem itself. I don't think that we have a big problem with efficiency, and I don't think that our problem space lend itself as well as the Go, where you have these the notion of local strategies as opposed to global strategies, that we have that in our Schnapsen example. So I think don't let yourself be distracted by now trying to think of deep learning for this. I think it is any good learning method will probably do. The question is, what do we want to learn? We have to understand the learning problem and have to translate it into something that we can make useful for our practical problem. So how are we doing this? The question is, what are our features? Is the one following the recipe, the machine learning recipe I introduced yesterday, and so we have to choose our features. And then for our Schnapsen application, we don't care that much about choosing the model and choosing the searching for a model, because that's sort of done by and automatically by our learning algorithm. But we have to choose the features and then apply them. So the general idea is that we apply learning in an offline way, as I suggested in the working sheet. We have basically 5 cards. And a lot of uncertainty. We don't know what our opponent has as cards. So there are many, so we have 5 opportunities, but then there are all these many belief states that we have to sort of take care of. And the decision we have to make is which of the cards to play is the best one. And now the idea is, let's do this by training. Let's look at many games that we can play. We can give it training examples by having our own bots play against each other, the random bot or the RD for the knowledge-based bots. And all you have to do is somehow build a classification set. Design that. First of all, a matrix, which contains on the one hand the features, and on the other hand, the outcome. Yeah? So one way of doing this is simply taking the 5 cards and say I have a table I take all the cards that are here, yeah, and I take the situation that I have the card here, and then I have this card, this card, this card, this card, and this card, and I put a value 1 here in my table. And now the question is, can I somehow say something about this card, this collection of cards winning or not? Basically, I have to do it, I have to do it with this situation. So once I played this card, what kind of feature space do I get? I have now a new situation. I played this card. Another question is, will I win the game or will I not win the game? And the way to do this is just to do some, in our case, I would suggest random rollout, for example, or you apply, you let 2 players play against each other. You have to somehow find out whether, given this position, your chances are higher to win or to lose. So basically, give your 2 bots this situation and have it play 20 times. And each time it plays, it writes down, it fills in a table and says, okay, first time I won, second time I lost, then I won again, and I won again, and so on. And if you have your bots play against each other, you will get a table like this, which you then can just add to your machine learning tool. Yeah. So basically what we want to do is to find a representation of the card game. Here there are 2 more features, namely my won points and opponent's points that you have already won. Maybe we can add more information, maybe we should take some information out. Some of the things are unknown in this, some of the things I know that they're in the pile and so forth. But the general idea is that we have a certain position after choosing a card. And the question is, do I win or do I lose? And then I just have to check the position given that I've trained a model, and this model gives me a prediction that this is better than this. This will win, this will win, this will lose, this will lose, this will lose. And then I can take one of those. So basically the algorithm to play the game is, once I have trained a model, I do the choose here, like I do with our deep or with the, what would be a hill climbing bot, where the hill climbing decision is taken by the model that gives us a value for how good it is. The choice is. So you can apply a regression model, or you can apply a classifier, whatever you want. And if you look at the working sheet number 3, then you see that in principle, we already provided this part, training a model, and we also provided one of the bots that applies a trained model on the decision process to make the decision between those different nodes. So this way we can apply machine learning in an offline way, so we have it play thousands of games against the bots that we have, then we know the outcome, and we can then use this for training. This is very close to the perfect information Monte Carlo, if you think about it, because in perfect information Monte Carlo, you just play the game randomly. You just have a random choice, which is faster, which is basically playing our R-deep bot. So if you play R-deep against each other, R-deep against R-deep, what you will get is perfect information Monte Carlo, unless I'm mistaken. Yeah? And that helps you to estimate over, and then you can learn from these random rollouts which of your moves is the best one. Okay, so there's a link, a page with links to different websites where you can play around with learning software. So we're now obviously not far enough, or not. This is not purpose of this lecture to get you towards developing new methods. That's something, that's something for the machine learning course. But you should now be able to understand enough to be able to apply those tools. And if you look at the working sheet, there are also links to the Python software, Python learning project package that you have to import. And then you can play around with this for training your data based on the features that you have. Remember what I said last time? This is sort of a trivial representation of the feature space, but it might make sense to make a design matrix out of it and add features such as combinations of those cards that you have. Choose specific ones, particularly the one with the, if you have a wedding, that is probably something that's very significant for the game. So just add a feature that checks whether you have the cards, or whether you have the cards queen and king of one color. Or trump cards. Maybe it's good to have per game sort of check whether your cards are trump cards and add them as a feature. So that's where you can start doing the exercises and where you can start doing experiments. Yeah?
Could feature all information about which moves are possible.
Sorry?
Because the game engine gives you the moves that you have possible.
Yes.
It does give you the weddings of jab swap.
Yes.
Inherently, so if you have more than 5 moves, then you obviously have a more price.
Yes, so you have more information through the game engine already because it also gives you the swap card and it gives you the weddings and so forth. So it's not always 5 choices that you have, so that was a bit simplifying things. Okay, so I will, after the break, I will